Imagine a world where scientists can design materials so precisely. They're like tiny, molecular Swiss Army knives, capable of capturing carbon, purifying water, or even breaking down pollutants. That's the promise of metal-organic frameworks, or MOFs. But here's the catch. There are millions of possible MOF structures, and testing them all manually is like searching for a needle in a haystack. That's literally the size of a galaxy. So how do researchers tackle this? For years, they'd painstakingly build MOFs from known building blocks, hoping to stumble on the perfect design. But now, a revolutionary tool is changing the game: generative artificial intelligence. Think of it like a creative assistant that doesn't just guess. It dreams up entirely new MOF structures. These AI models, like variational autoencoders or diffusion models, learn from existing MOF data and then generate candidates that meet specific goals, like high gas storage or stability. It's like teaching a computer the grammar of MOF chemistry, then letting it write its own molecular poetry. But here's where it gets even cooler. These AI-generated ideas aren't just theoretical. They're tested using high-speed simulations and even robotic labs that synthesize and analyze the materials automatically. It's a closed-loop system. AI proposes a structure, computers validate it, and robots build it, then feed the results back into the AI to refine the next round. Take the example of DiffLinker, a model that focuses on the organic linkers in MOFs. By tweaking these molecular stitches, it can design MOFs with ultra-high carbon capture potential. Or MOFFUSION, which uses math to map out pore structures, ensuring the materials are not just novel but also chemically sound. Yet challenges remain. Can these AI-generated MOFs actually be made in a lab? Are the datasets diverse enough to avoid bias? And how do we balance creativity with the real-world constraints of chemistry? The future. Imagine AI-designed MOFs that harvest water from desert air, or trap methane emissions with unmatched efficiency. This isn't science fiction, it's the next frontier of materials science. And as these tools evolve, they're not replacing scientists, they're empowering them to solve problems we've only just begun to imagine. So the next time you hear about breakthroughs in clean energy or environmental tech, remember, behind the scenes, AI is helping design the tiny, powerful materials that could change our world. Stay curious and let's keep exploring the future, together. Let's dive deeper. MOFs are like molecular sponges, built by connecting metal ions with organic molecules to form ultra-porous structures. Their tiny maze-like pores can trap gases, filter chemicals, or act as catalysts. But designing the perfect MOF used to be like searching for a needle in a haystack. Traditional methods relied on trial and error, which could take years. But what if we could predict the best MOF designs before ever setting foot in a lab? That's where AI steps in. Researchers are now using machine learning models to simulate and optimize MOFs, slashing development time from decades to days. Here's how it works. AI models like generative diffusion models and transformers, yes, the same tech behind chatbots, are trained on vast databases of existing MOFs. These models learn the rules of molecular architecture, then generate entirely new structures with desired properties, like ultra-high porosity or stability under extreme conditions. Take MOFDiff, which uses diffusion processes to predict MOF behavior, or MOFFLOW, which simulates how pores expand and contract to adapt to environments. Even more groundbreaking. Some models now decode how MOFs breathe, a critical feature for gas storage and sensing applications. The results? Imagine MOFs that capture carbon emissions from power plants, sensors that detect pollutants in real time, or drug delivery systems that release medicine only where it's needed. But the real magic lies in AI's ability to invent structures no human has thought of. One project used Bayesian optimization, a statistical technique, to cut down the time needed to find optimal MOF candidates by orders of magnitude. Others combine AI with lab automation, creating self-driving experiments where the computer suggests a synthesis method, the robot tests it, and the AI learns from the results. Of course, there are hurdles. AI relies on data quality, and some models still struggle with chemical reality. But the progress is undeniable. From predicting MOF gas interactions to designing materials that harvest water from air, these tools are pushing boundaries. So the next time you hear about AI in science, remember, it's not about robots taking over. It's about amplifying human ingenuity, accelerating solutions to global challenges, and unlocking the next generation of materials that could change everything, from energy to medicine. Stay curious, and let's keep exploring the science that's rewriting the rules of discovery.